Hello, today we are going to talk about exponential functions and the type of explosive growth that they can model. The exponential function f with base b is denoted by f of x equals b to the x power. The b has to be a positive number other than 1, but the x can be any real number. So the base is a constant number. The exponent is a variable for an exponential function. In previous math courses, you've encountered positive and negative integer and fractional exponents. Recall, for example, that 2 raised to the power minus 3 is the same thing as 1/2 raised to the power 3, or 1/2 cubed. That would be 1/2 times 1/2 times 1/2, which is 1/8. What about a fractional exponent? Well, for example, 64 raised to the power 2/3 is defined to be the cube root of 64, that quantity squared. The cube root of 64 is 4, so 4 squared is 16. 64 to the 2/3 power is 16. But in the definition of an exponential function that we just gave, we said the exponent x could be any real number. What would be the meaning of an irrational exponent? To answer that question, think about this example. Suppose you had some base b raised to the power square root of 2. What would that mean? Think about the decimal approximations for square root of 2 that are getting more and more accurate as you carry the decimal approximation out to further places. B to the 1.4, B to the 1.41, B to the 1.414, and so forth. Those values of the base b raised to these rational decimal exponents, as the decimal approximation becomes closer and closer to the square root of 2, that limiting value can be thought of as what we mean by b raised to the power square root of 2. Think about the exponential function f of x is 2 raised to the power x. Compare or contrast that with the polynomial quadratic function g of x is x squared. Notice with the exponential function, the base is a constant and the exponent is a variable. With the quadratic function, the base is the variable and the exponent is the constant. If you evaluate f of 30, that would be 2 raised to the power of 30. And that turns out to be 1,073,741,824. On the other hand, g of 30 would be 30 squared, which is just 900. Wow, what a difference. You can see that exponential functions can model extremely rapid explosive growth, much more so than a quadratic function. Let's look at a graph of f of x equals 2 to the power x. 2 to the minus 3 would be the same thing as 1/2 cubed, which is 1/8. 2 to the minus 2 power would be 1/2 squared, which is 1/4. 2 to the minus 1 power would be 1/2 to the first power, or just 1/2. 2 to the 0 power is defined to be 1. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8, and so forth. This graph would have the exact shape of an exponential function. F of x is b to the power x if my base b is some number greater than 1. I use 2 as the example. Notice that the domain is the set of all real numbers. I can substitute any real number for the exponent x, but the range is the set of positive real numbers. Notice that the curve always lies above the x-axis. There is no value of x that you could substitute in so that 2 to the x would equal 0. It gets closer and closer to 0 as x goes toward minus infinity, but it never equals 0. There are no x-intercepts, but the y-intercept is 0, 1. Again, if x is 0, 2 to the 0 power equals 1. So the point 0, 1 is going to be on the graph of these exponential functions. As we said, the x-axis is a horizontal asymptote. As x approaches minus infinity, b to the x is going to get closer and closer to 0. The graph is increasing as you move from left to right. It is a one-to-one function. You can see that it passes the horizontal line test. The point 0, 1 is on the graph, as we've said. The point 1, b, in this case, our b is 2, so the point 1, 2 is on the graph. The point minus 1, 1 over b. In our case, minus 1, 1 over 2, or minus 1, 1/2 is on the graph. The graph is smooth and continuous with no corners or gaps. Contrast this graph with the one on the right where f of x is 1/2 to the power x instead of 2 to the power x. Here our base is a fraction that's less than 1. The domain is the set of all real numbers. Once again, I can have any real number as my exponent. Again, the range is the set of positive real numbers. Let's look at some points on this graph. If x is minus 3, 1/2 to the minus 3 power is the same thing as 2 cubed, or 8. 1/2 to the minus 2 power is the same thing as 2 squared, or 4. 1/2 to the minus 1 power is the same thing as 2 to the first power, or 2. 1/2 to the power 0 is again defined to be 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8, and so forth. You can see once again there are no x-intercepts. The y-intercept is still 0, 1. The point 0, 1 is on both of these graphs. Again, the x-axis is a horizontal asymptote, but this time it's as x approaches infinity that f of x is approaching 0. This graph is decreasing as you go from left to right. This graph is also one-to-one. It passes the horizontal line test. And we have the point 0, 1 on the graph. 1, 1/2 in this case is on the graph. Minus 1, 2 is on the graph for this case where we are using 1/2 as the base to the power x. The graph again is smooth and continuous with no corners or gaps. We want to talk about another base, the base e. This is called the natural exponential function. E is an irrational number. Its decimal approximation is approximately 2.71828, and it goes on forever without repeating. It's called the natural base. You might be wondering, why would such an irrational number be called a natural base? It turns out that E is an irrational number that occurs in all kinds of natural applications. You can think about pi is also an irrational number that you know occurs quite frequently in a lot of mathematical problems. E does as well. E is the limit as n approaches infinity of this expression 1 plus 1 over n raised to the power n. If you look at this chart, I've taken n to be 1, 2, 5, 10, 100, 1,000, 10,000, 100,000, a million, and so forth. N is approaching infinity. And as you substitute all of these values for n into this expression 1 plus 1 over n to the power n, if you look in the last column, you can see that the result is getting closer and closer to a limiting value. That limiting value is defined to be the irrational number e. Here are some applications for exponential functions. If you put money in the bank and it's paying you an interest rate compounded n times per year, and you want to know how much money will you have, the amount that is in the account after T years is given by this formula. The principal, or your original deposit, multiplied by 1 plus R over N, where R is the interest rate expressed as a decimal, N is the number of times per year that the interest is compounded, and the exponent is N times T. T is the time in years. What if your interest is compounded continuously? Then the amount in the account is given by this formula. The original principal times this irrational number E raised to an exponent R times T. Once again, R is the annual interest rate expressed as a decimal, and T is the time in years. Let's look at an example problem. Suppose I start out with an original deposit of $2,500 and I'm earning an interest rate of 4%, and I want to leave my money in the account for 20 years. And I want to calculate how much money will be in the account after 20 years if it's compounded n times per year. What if it's compounded annually, once a year, or compounded twice a year, semi-annually, or compounded 4 times a year, compounded quarterly, compounded 12 times a year, would be compounded monthly, compounded 365 times a year, compounded daily, and eventually, what if it were compounded continuously? For n equal to 1, 2, 4, or 12, I'm going to use this formula. The amount in the account after 20 years is the original deposit, $2,500, times 1 plus the interest rate, 4% is 0.04, divided by the number of times it's compounded per year, n, raised to an exponent of 20 times n if it's in there for 20 years. So I simply substitute for the n 1, and then substitute 2, 4, 12, and finally 365. If you enter that in the calculator, you get the amount shown in the table here. Notice that the more frequently the interest is compounded, the larger the amount that will be in the account. If it's compounded continuously, I have to change my formula. The amount would be the original deposit, $2,500, times this irrational number E raised to an exponent. The exponent is RT. T is 20 years. The rate is 4%. 0.04 times 20 is 0.8. So if you enter into your calculator 2,500 multiplied by the irrational number E raised to an exponent of 0.8, you get $5,563.85, rounded to the nearest penny, would be in that account after 20 years. Let's look at another example problem. Suppose after T years, the value of a wheelchair conversion van that originally cost $49,810 depreciates so that each year it's worth only 7/8 of its value for the previous year. Instead of exponential growth, this is going to be an exponential decay. The value is going to be going down. We want to find a model for the value of the van after T years, V of T, and then determine the value 4 years after it was purchased. When T equals 0, the value is this initial $49,810. After 1 year, when T equals 1, the value would be $49,810 times 7/8. When T is 2, after 2 years, it's going to be $49,810 times 7/8 times 7/8 again. So our model, V of T, is $49,810 times 7/8 raised to an exponent of T. If I want to know the value of the van after 4 years, it's $49,810 times 7/8 to the fourth power. If you use your calculator and round to the nearest cent, you find the value of the van after 4 years is only $29,197.71. It has depreciated as it's gotten older. Here is an example of exponential growth. Let's say that a bacteria culture contains 1,500 bacteria initially, and it doubles every hour. Find a function, n of t, that models the number of bacteria after t years. Well, n of t would be my initial number, 1,500, times 2 raised to an exponent of t, where t is in hours. So if t is 0, 2 to the 0 power is 1. 1 times 1,500 is 1,500. That's my initial amount. If after 1 hour, it's going to double. So 2 to the first power is 2. 2 times 1,500 would be 3,000, and so forth. Find the number of bacteria after 24 hours. I'm merely going to substitute 24 for the t here. And when I do that, 1,500 times 2 to the 24th power is 25,165,824,000 bacteria after only 24 hours, when we only started with 1,500, but we were doubling every hour. This is a good example of exponential growth. You see how rapidly something can grow if it is modeled with an exponential function.